Welcome. Today, we're going to crack open the Data Detective's Toolkit. We're going to learn how to hunt for clues hidden in data and see how two completely different things in our world might actually be connected.
So, let's just dive right in with a question I bet you've thought about. Does all that time on your phone or laptop actually lead to lower grades? I mean, it kind of feels like it could be true, right? But how do we go from just a hunch to having some real evidence? Well, solving mysteries just like this one is exactly what we're here to do today.
All right, so where does any good investigation begin? You've got to identify your key players, or in our case, the suspects. Before we can even start looking for a connection, we have to be crystal clear about what we're looking at.
Now, in the world of data, our suspects are called variables, and they come in two main flavors. You've got the explanatory variable. That's the one we think might be causing all the action. And then you have the response variable. That's the outcome, the thing we're measuring. Really, just think of it as the potential cause and the potential effect.
And here's a super simple way to keep them straight. The explanatory variable, our potential cause, always goes on the bottom of the graph, the horizontal x-axis. The response variable, the effect, goes up the side, on the vertical y-axis. So if we're looking at studying, the hours of study goes on the bottom, and the exam score you get is the response that goes up the side. Simple as that.
So, what we're hunting for, our very first clue, is something called an association. All that means is that if we know the value of one variable, it gives us a hint about the value of the other. It doesn't prove anything yet, but it tells us that these two things seem to be moving together in some kind of pattern.
Okay, so we've identified our variables, but how do we actually see if they're connected? This brings us to the first and, honestly, most important tool in our kit. Let's build our case by actually looking at the evidence.
And this right here, this is a scatter plot. It's basically the data detective's #1 tool, their magnifying glass. It's such a powerful idea. Every single dot on this graph is one person or one thing from our data. It shows us two things about them at once. It literally turns a boring list of numbers into a picture we can investigate.
So when you're staring at one of these, what are you looking for? The first thing you ask is, what's the overall direction? Does the whole cloud of points seem to be drifting upwards, from left to right? That's a positive association. Or is it drifting downwards? That's a negative one.
Next up, you gotta ask about the form. Are all those little dots bunching up to make something that looks kind of like a straight line? Or is there maybe a curve to it? For most of what we're doing, we're on the lookout for a linear form, something that follows a straight path. And, last but not least, we need to figure out the strength. How closely do all those dots hug that line or curve? If they're all packed together in a tight, neat pattern, we've got a strong relationship. If they're spread all over the place like a vague cloud, it's pretty weak.
Oh, and here's a super important pro tip for any detective work. Always be on the lookout for the odd one out. We call these outliers. They're the points that just don't fit the main pattern. They can be really interesting stories on their own, but they can also totally mess up our analysis, so we've got to spot them.
Looking at a picture is a great start, but a real detective needs hard evidence, right? A gut feeling isn't enough. We need to quantify what we're seeing. We need a number.
And that number, my friends, is the correlation, which we just call R. It's this incredibly elegant little statistic that pulls double duty. It tells us both the direction and the strength of a relationship. But, and this is important, only for linear relationships. It's a real powerhouse tool.
So how do you read this R value? It's actually pretty simple. If R is positive, the relationship goes up. If R is negative, it goes down. The closer that number gets to either 1 or -1, the stronger that straight line relationship is. And if it's hovering around 0, that means there's a really weak linear connection, or maybe none at all. And just like before, watch out for those outliers. They can grab this number and change it dramatically.
Okay, everybody, lean in for this one. If you only remember one thing from this whole explainer, please make it this. Just because two things have a strong association, it does not mean that one causes the other. For example, ice cream sales are strongly correlated with shark attacks. But does eating a scoop of mint chip make a shark bite you? No, of course not. There's a hidden variable, hot summer weather, that causes both to go up. So say it with me, association is not causation.
Okay, so we've found a connection. We've measured it. Now for the really fun part, using what we've learned to try and predict the future. It's time to build a model.
And our crystal ball, in this case, is called a regression line. Just think of it as the perfect line of best fit that we can draw right through the middle of our cloud of data points. Its whole job is to give us a prediction for y, we call it y hat, for any x we want to plug in.
That little hat on the y just means it's a prediction, not the real thing. So let's not get scared by the formula. It's actually super straightforward. The b part is the slope. This is so useful. It tells us for every one-step increase in x, how much we predict y will change. The a is just the y-intercept. That's our starting point. It's the predicted value for y way back when x is 0. Now, a really important warning here. Our fancy prediction line is only trustworthy for the range of data we actually saw. Trying to make predictions way outside that range is called extrapolation, and it's like driving off the edge of your map. It's dangerous and almost always gives you crazy, unreliable answers. Stick to the evidence you have.
All right, we've built this shiny new prediction machine, but how do we know if it actually works? Is it a high-tech tool or just a piece of junk? A good detective always checks their work. It's time for a reality check.
The way we check our model is by looking at its mistakes. And in statistics, we have a fancy name for those mistakes, residuals. A residual is just the leftover bit. It's the gap between a real data point and where our line predicted it would be. It's the part of the mystery our model couldn't quite solve.
And what we do is we plot all those little leftovers. What you want to see is, well, nothing. A beautiful, random, boring mess of dots. That's a great sign. It means our straight line model did a good job. But if you see a leftover pattern, like a curve, that's a huge red flag telling you that a linear model was the wrong tool for this mystery.
Okay, we're at the finish line. There's one last number we need, and it's kind of like the final score for our model. It's the coefficient of determination, or just r squared. All it tells us is what percentage of the story our model actually explains.
So, what does that actually mean? Well, if we get an r squared of, say, 78%, it's like saying this. 78% of the variation we see in exam scores can be explained by the number of hours a student studied. That tells us our model has some real predictive power. The other 22%, that's just variation caused by all the other stuff in life we didn't measure.
And there you have it. That's the whole Data Detectives toolkit. We went all the way from asking a question to seeing the pattern, measuring the link, building a model to predict with, and even checking our own work. So now that you've got the tools, what relationship out there in the world are you going to investigate first?